This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on partial derivatives and min-max problems. So our first example is to find all of the first and second order partial derivatives for this function. F of xy is 2x squared y cubed plus 3x to the fourth plus 5x e to the y. Our first order partials will be the partial of f with respect to x and the partial of f with respect to y. That's what we're going to start with. So to find the partial of f with respect to x, we look at this notation, f sub x, or this d dx of f, this sort of odd-looking d. That's the notation that we use for the partial derivative with respect to, in this case, partial with respect to x. In that instance, we perceive of functions of y as constants. X is changing, y is perceived to stay the same. That is the process we'll use to find the partial derivative of f with respect to x. So we're looking at our function. F of xy is 2x squared y cubed plus 3x to the fourth plus 5x e to the y. We want to find the partial of f with respect to x, using that notation, funny looking d with respect to x of that whole thing. Now, the derivative of the sum is the sum of the derivatives. We know that from earlier work. The same thing is true for the partial derivative. So the partial derivative of the sum, these three pieces, will be the sum of the partial derivatives. The partial derivative of the first piece, plus the partial derivative of the second piece, plus the partial derivative of the third piece. Now looking at this, what do we see? We take our partial derivative of the first piece, 2x squared y cubed, plus the partial derivative of the second piece, 3x to the fourth, plus the partial derivative with respect to x of 5x e to the y. Now, x is perceived as our variable. So in this case, y cubed is perceived as a constant. 2 is perceived as a constant. So both 2 and y cubed can come out in front of that partial derivative operator. This second thing, 3x to the fourth, is just a function of x. If that's the case, the partial derivative is the same as the regular derivative. And this third piece, partial with respect to x of 5x e to the y. E to the y is perceived as a constant. Any function of y is perceived as a constant. Obviously 5 is a constant, so 5e to the y can come out in front of the derivative operator. So you'll see how that happens. The 2y cubed came out in front of this partial with respect to x. Now I just have partial with respect to x of x squared. The second one is a function of x, so no need to move anything out. In this third piece, both 5 and e to the y are acting like constants. 5e to the y comes out. Partial derivative with respect to x of x. Each one of these things in parentheses now are functions of x alone. Once that happens, the partial derivative behaves like the regular derivative. So the partial with respect to x of x squared is the same as the derivative with respect to x of x squared, which is 2x. For this piece, partial with respect to x of 3x to the fourth, same as derivative with respect to x of 3x to the fourth, which will be 12x cubed. Partial with respect to x of x, same as the derivative with respect to x of x, which is just 1. So we'll see how that works. Derivative with respect to x of x squared is 2x here. 3x to the fourth will give me 12x cubed here. Derivative with respect to x of x is 1. And then simplifying this, what do we get? 2x times 2y cubed, 4xy cubed, plus 12x cubed, 5e to the y times 1 is 5e to the y. And that is our partial derivative with respect to x of that function f. Now we can also take partial derivatives with respect to y. So looking at our same function, now our goal is to find f sub y, the partial derivative with respect to y of f. So what we'll do there is the same thing we did before, namely take the partial with respect to y of the first piece plus the partial with respect to y of the second piece plus the partial with respect to y of the third piece. Now how do we do the partial with respect to y of 2x squared y cubed? As far as y is concerned, 2x squared is a constant. That will come out in front of the partial with respect to y sign. The partial with respect to y of 3x to the fourth, well, that is just a function of x. Partial with respect to y tells us that x acts like a constant. So x to the fourth is essentially a constant. 3 is essentially a constant. The derivative of a constant is 0. So the partial with respect to y of 3x to the fourth will be 0. The partial with respect to y of 5x e to the y, now e to the y is our variable of interest, so 5x is perceived as a constant. That can come out in front of the partial derivative sign. So we'll have the partial derivative with respect to y of e to the y times that constant 5x. Pulling out the 2x squared and pulling out the 5x, you can see now this thing is just a function of y. So the partial with respect to y of y cubed will be the same as the derivative with respect to y of y cubed. There's only one variable here of interest. The derivative with respect to y of y cubed, of course, is 3y squared. Same thing here. The derivative with respect to y of e to the y is the same as the partial derivative with respect to y of e to the y, which will just be e to the y. But this middle piece is going to be 0. Because again, x to the fourth is acting like a constant, as is 3, and the derivative of a constant is 0. Which brings us here then, so we get our 2x squared times the partial with respect to y of y cubed is 3y squared. The partial with respect to y of a function of x will be 0. 5x, the partial with respect to y of e to the y will just be e to the y. And then simplifying that, what do we get? 2 times 3, 6, x squared y squared plus 5x e to the y is our partial with respect to y. So f sub x and f sub y in this case are first order partial derivatives. We can also find second order partial derivatives. So a partial derivative of a partial derivative. So this is our function of interest. F of xy was 2x squared y cubed plus 3x to the fourth plus 5x e to the y. And our goal now is to find f sub xx. So we first do a partial with respect to x, that's what the first x represents. Then we do a partial with respect to x again, that's what the second x represents. So I will use this notation, f sub xx is the partial with respect to x of f of x. Now we showed that the partial with respect to x was 4xy cubed plus 12x cubed plus 5e to the y. If I want f sub xx, I've got to take the partial derivative with respect to x of this function. So indeed, partial with respect to x of 4xy cubed plus 12x cubed plus 5e to the y. What do we do here though? The derivative of the sum is the sum of the derivatives. So our strategy will be to take the partial with respect to x of this piece plus the partial with respect to x of this piece plus the partial with respect to x of that piece. Now what is perceived as a constant here? X is our variable of interest. So in this first piece, both 4 and y cubed are perceived as constants. They can come out in front. In my second piece, this is just a function of x. In that case, the partial derivative acts like the regular derivative. And in the third piece, this is just a function of y. And as far as x is concerned, y behaves like a constant. 5 is a constant, and a derivative of a constant is going to be 0. So putting all that together, what do we get? We pull the 4y cubed out in front, because that's perceived as a constant. This thing is just a function of x, so I'm going to leave it alone. This thing is just a function of y, so I'm going to leave it alone. But the partial with respect to x of x is 1. The partial with respect to x of 12x cubed is the same as the derivative with respect to x of 12x cubed, which is going to give me 36x squared, plus the partial with respect to x of a function of y. If this is acting like a constant, the partial with respect to x of a constant would just be 0. Simplifying this, we have fxx is going to be 4y cubed times 1 plus 36x squared, or 4y cubed plus 36x squared. So fxx means first take a partial with respect to x, then take another partial with respect to x. That's what our f sub xx, second order partial, represents. Now let's do another one. Let's take a look at f sub yy. So what that means is you take first the partial with respect to y, and then you take the partial derivative with respect to y of that partial derivative with respect to y. This was our original f of x, y. The partial with respect to y we showed was 6x squared y squared plus 5x e to the y. If I want f sub y, y, I will take the partial derivative with respect to y of that piece. So indeed, f sub y, y, partial with respect to y of f sub y, partial with respect to y of this. Take the partial with respect to y of the first piece plus the partial with respect to y of the second piece. Now what are our constants here? Y is our variable of interest. So as far as y is concerned, 6x squared is a constant. That can come out in front of your derivative operator, your partial derivative operator. Y is our variable of interest, so e to the y is a function of y. 5x is perceived as a constant. That can come out in front of your derivative operator. So pulling out the 6x squared, pulling out the 5x, now we have f sub y, y is 6x squared times the partial with respect to y of y squared plus 5x times the partial with respect to y of e to the y. But when these are just a function of one variable, partial with respect to y of y squared, partial with respect to y of e to the y, it is the same as a regular derivative. So the partial with respect to y of y squared is 2y. The partial with respect to y of e to the y is e to the y, since again they're acting as derivatives. So we get 6x squared times 2y plus 5x, the derivative of e to the y is e to the y. Simplifying this, 6 times 2, 12x squared y plus 5x times e to the y gives us fyy. But there are still two more types of partial derivatives we can look at. So if we have our f of x here, our f sub x is 4xy cubed plus 12x cubed plus 5e to the y. What else can we do other than fxx? We can look at something called f sub xy. That would be the partial derivative with respect to y of f sub x. Partial derivative with respect to y of all of these guys. So the derivative of the sum is the sum of the derivative, partial of the first plus partial of the second plus partial of the third. Now what are our constants here? As far as y is concerned, 4x is a constant. That's only a function of y, and that's only a function of x. So the only thing I can really pull out here is the 4x. So I have 4x times the partial with respect to y of y cubed, plus the partial with respect to y of 12x cubed, that's a function of x, perceived as a constant. Derivative of a constant is 0. Partial with respect to y of 5e to the y, that is just a function of y, so now this behaves like a regular derivative. The derivative with respect to y of y cubed is 3y squared, so that'll be 4x times 3y squared. The derivative of what is perceived to be a constant will be 0. And this is just a function of y, so the partial with respect to y of 5e to the y is the same as the derivative with respect to y of 5e to the y, which is just, of course, 5e to the y. So what does that give me? 4x times 3y squared, the derivative of y cubed, plus the partial of a function of x with respect to y is just going to be 0. And then the partial with respect to y of 5e to the y will be 5e to the y. Adding these things together, what do we get? 4 times 3 is 12, xy squared, plus 5e to the y is our f of xy. So we've done f sub xx, we've done f sub yy, and we've done f sub xy. On the next video, I'm going to do f sub yx, which is first take the partial with respect to y, and then take the partial with respect to x, and we'll see something interesting about that.